look around you. Your smartphone, your laptop, even that smart thermostat on your wall, they all share something invisible but fundamental: integrated circuits, or chips.
Hmm.
These tiny things, often packing billions of components, are really the heart of our digital world. But have you ever stopped to think, considering that immense complexity, how these intricate systems actually come to life?
Yeah.
Historically, designing them was almost like a painstaking craft, building at the individual transistor level. Sounds meticulous, but incredibly limiting.
And that approach became utterly unmanageable, didn't it?
Yeah.
Just completely impractical as chips got more and more complex.
Right.
Handling billions of individual components, their connections.
Mm.
Doing that by hand, impossible. This escalating complexity was really the fundamental force driving the whole evolution of digital design abstraction.
The abstraction,
Well,
okay.
because here's the hard truth, and the industry learned this the hard way.
Mm-hmm.
Any error you find after a chip is manufactured is catastrophic.
Right, you can't just patch it.
Exactly. No software patch here. It means a complete redesign, remanufacturing. We're talking exorbitant costs, huge delays, often enough to kill a project entirely.
Which brings us neatly to today's deep dive.
Mhm.
We're unraveling the world of register transfer level, or RTL.
Yep.
And it's absolutely critical, often unsung partner verification. Think of it as a journey into the blueprint of digital circuits, and then crucially, how we make sure that blueprint translates into something that works perfectly every time. So our mission today is to demystify RTL, understand why it's become this sort of sweet spot in modern chip design, and really reveal the monumental effort of verification that ensures all our smart devices actually, well, work.
And by the end of this, you'll have a much clearer picture of this hidden world behind the chips powering everything. We'll uncover some surprising facts and critical insights into how these technological marvels are built and, just as importantly, validated. We want what's called first-pass success.
So that sheer unmanageable complexity, that's really what kicked off this whole evolution towards automation, right?
Exactly. It wasn't just automating tasks. It was a fundamental conceptual leap. Without sophisticated electronic design automation, EDA, tools today, well, creating modern chips with billions of elements would be flat out impossible.
Just couldn't do it.
Couldn't do it. The shift from that sort of craftsmanship to a systematic engineering discipline wasn't optional. It was a pure necessity.
And it was right in the middle of this evolution, the shift, that register transfer level design, RTL, really solidified its place as the central step, the sweet spot, as you said.
It is the sweet spot for several really compelling reasons. First, it offers just the right level of abstraction. It bridges the gap between high-level system specs and the detailed circuit implementation.
Okay.
So engineers can focus on higher-level functions, and this is critical optimized for power, performance, and area PPA at a very early stage.
Which saves money, I assume.
Oh, it's a massive economic advantage. Imagine making a design change when it's just lines of code versus when it's, already physically laid out.
Yeah, that sounds expensive.
Changes at the physical layout stage are exponentially more costly. So validating and refining architectural decisions early, when they're cheapest to modify, saves huge amounts of time and money. Plus, RTL is the standard input for the automated synthesis tools. It's the blueprint they follow.
Okay, so what is RTL design specifically? Like, what does it actually look like day to day?
At its core, RTL models a synchronous digital circuit. It focuses primarily on the flow of data between hardware registers.
Right, the storage spots.
Exactly, the storage spots. And the logical operations performed on that data as it moves. The phrase register transfer literally tells you what it's about: moving data between registers and transforming it along the way.
So you're thinking about the data flow, how it gets modified, not really the tiny details of individual transistors at this stage.
Precisely. It's a behavioral model that implies a structure. You're specifying how data flows and transforms over these discrete time intervals, synchronized by a clock.
It's like the choreography for the data.
That's a good way to put it. And to define this choreography, you have some core components. First, registers.
Yeah.
The actual memory elements, usually D flip-flops, synchronized to that master clock. They're the only things holding state.
Okay.
Then you have combinational logic, circuits doing the actual work, ANDs, ORs, adders, multipliers. Their output depends only on the current inputs. No memory there.
Got it. Logic happens instantly, registers hold the result.
Pretty much.
Huh.
The clock signal is the conductor, telling everything when to move data between registers, ensuring predictable timing. And often you use finite state machines, FSMs, as control structures, defining system states and transitions.
Right, controlling the sequence of operations.
Exactly. And sticking to synchronous design principles is key for making the rest of the design flow smoothly. If you have to use asynchronous logic, you need to isolate it very carefully.
And these abstract models, this RTL design, you write them using special languages, right? Hardware description languages, HDLs, like Verilog and VHDL.
That's right. HDLs like Verilog and VHDL let you declare hardware elements, like registers. They kind of look like variables in software.
Sort of, yeah.
And then describe the combinational logic using familiar things like if-then-else statements or math operations. What's really interesting, especially in Verilog, is this key difference between blocking and non-blocking assignments.
Okay.
A blocking assignment happens immediately, like in software, but a non-blocking assignment schedules the update for the end of the current clock cycle. That little difference is absolutely crucial for correctly modeling how synchronous hardware actually behaves in parallel.
Ah, subtle but important for timing.
Very important.
So RTL is this incredible blueprint, but like you said, it's just one piece of a much bigger process. The ASIC design flow, application-specific integrated circuit, it's like a whole journey for the chip.
It really is a rigorous multi-stage process. It's iterative, lots of trade-offs between PPA power, performance, area. You typically start with chip specification.
Defining what it needs to do.
Exactly. Features, microarchitecture, performance targets, timing, area, power, speed. And given design cycles can be long, like 6 months to 2 years.
Wow.
You have to anticipate future trends. That spec is the bedrock.
Okay, what's next?
Then comes ASIC architecture, figuring out the high-level structure. Then logic design, that's our RTL coding. And running parallel to that is verification, then synthesis, physical design, and finally, more verification at the end.
And RTL is in that front-end part, so after specification comes.
Design, entry, and functional verification. This is where the design team actually writes the RTL code, and crucially, the verification team simultaneously develops the test environment, the test bench.
So coding and testing start together.
Pretty much. You need to confirm the logic works as intended right away using simulation. Teams aim for high code coverage, often like 95% or more, just to show they've exercised most of the code.
Okay, now here's the stat that really surprised me when I first heard it. You mentioned RTL coding, but you said verification is, what was it, 80 or 90% of the effort?
Yeah, it often works out that way. The RTL coding itself might only be 10–20% of the total design cycle time and resources. Verification consumes the vast majority, 80, sometimes even 90%.
That seems wildly disproportionate. Why so much effort on verification?
It sounds crazy, right? But think back to what we said about errors found after manufacturing.
Catastrophic costs.
Yeah.
Huge delays.
Exactly. A single bug escaping into silicon can mean tens of millions of dollars and months lost for a respin. It's the ultimate pay me now or pay me way more later situation. Investing heavily in verification up front, even if it looks like overkill, is absolutely essential to minimize that risk and hit first-pass silicon success. You really want the first batch of chips to work.
Okay, that makes sense. Pay now or pay devastatingly more later. So once the RTL is coded and initially checked, it moves to the back end. And the first step there is synthesis.
Correct. Synthesis is the pivotal step, bringing the front end, abstract design, and the back end, physical implementation.
So what does synthesis actually do?
It's an automated process. It takes the high-level RTL code written in Verilog or VHDL and translates it into a gate-level netlist.
A netlist, like a list of actual logic gates.
Precisely. It's a detailed description of the circuit using basic logic gates, ANDs, ORs, flip-flops from a specific technology library, and how they're all interconnected. It makes the abstract design concrete and ready for the physical layout stage.
And why is this translation so vital?
Because it bridges that abstraction gap. It also optimizes the design to meet those critical PPA targets before you commit to the expensive manufacturing process. It ensures the design is actually buildable and will meet performance specs. Synthesis typically involves three main stages. First, translation, converting the HDL into generic technology-independent logic cells. Then, optimization, refining the logic to meet PPA goals. This is where a lot of magic happens. And finally, mapping, matching that optimized logic to the specific physical cells available in the Foundry's library.
So it tailors the generic design to the actual factory process.
Exactly. And during synthesis, other important things happen, like inserting clock gating logic to save power.
Turning off parts that aren't being used.
Yep. And design for testability or DFT structures like scan chains, which are crucial for testing the manufactured chips for defects.
And I think I read about physical aware synthesis. Does that make it even better?
It does. That's a more advanced form that pulls in information about the chip's physical layout, like the floor plan, during synthesis. This helps it make smarter optimization choices, leading to better PPA results and better correlation between predicted timing and actual timing later on. Saves headaches down the line.
Okay, so this brings us back really to digital IC verification, the unsung hero consuming, as you said, 80–90% of the effort, the safety net.
Absolutely, the safety net. And you really need it. Undiscovered bugs aren't just minor annoyances. They can cause performance nightmares, make products unusable, or in critical systems like automotive or medical.
Yeah, safety becomes a huge issue.
Exactly. Significant safety threats, system failures, massive financial losses, damage to a company's reputation. It's serious stuff. That's why the industry mantra is find bugs as early as possible.
Because fixing them later gets exponentially harder and costlier.
Exponentially. Every step a bug travels down the design flow gets much harder, it takes much longer, and costs much more to find and fix.
So how is this massive verification task broken down? Are there different kinds?
Oh yeah, there are several layers. You've got functional verification. Does the chip behave according to its specification? This often uses simulation, but also formal verification, which uses mathematical methods to prove certain properties.
Okay, proving correctness mathematically.
Right. Then there's logic verification. Are the gates connected correctly? Does the synthesized netlist match the RTL? This involves things like equivalency checking and static timing analysis.
Checking the translation was done right.
Basically, yes. Then physical verification. Does the final chip layout obey all the manufacturing rules? That's design rule checking, DRC, and layout. Versus schematic, LVS, to make sure the layout matches the netlist.
Checking against the factory's rules.
Even after all that, once you have the actual silicon chips back, there's post-silicon validation, testing the real hardware for any remaining defects or issues that simulation might have missed.
Wow, layers upon layers of checking, and presumably this all starts with some kind of plan.
Oh, absolutely. It has to. It starts with a verification test plan. This is a meticulously crafted, detailed document, and it's a living document. It evolves.
What goes into that plan?
It covers three main things. What to verify, detailing every feature, configuration, corner case, how to verify, outlining the best methods, what kind of stimulus to use, how to check results, and when to verify. Estimating effort, setting priorities, because you never have infinite time.
Right, you have to prioritize.
Always.
Yeah.
And this plan needs constant updates and reviews as the design changes or you learn more. It's the roadmap for the entire verification effort.
So with the plan in place, you build the test environment, the test bench. And you mentioned hardware verification languages. HVLs like System Verilog are key here.
They became essential. Traditional HDLs, like Verilog itself, could be used for simple test benches, but they really struggled as designs got super complex.
They weren't built for verification, really.
Not for modern verification complexity. HVLs like System Verilog were developed specifically to tackle this. They offer much more powerful features: object-oriented programming, better randomization control, built-in functional coverage, things you desperately need for complex verification.
And building on System Verilog, there's this thing called UVM, the Universal Verification Methodology.
Yes, UVM is huge. It's a standardized methodology built on System Verilog, specifically for creating robust, reusable, and scalable verification environments for today's incredibly complex chips.
Standardized, reusable sounds like big benefits.
Massive benefits. Reusability means you can leverage components across projects, saving time. Scalability means the approach works for small blocks up to giant systems on chip. Modularity helps organize the complex test bench structure. All this leads to much greater productivity for verification teams.
How does UVM achieve all that? What are the core ideas?
Well, it heavily leverages object-oriented programming from System Verilog for that modularity and reuse. A key technique is constrained randomization. Instead of writing specific tests one by one.
Which would take forever.
Forever. And you'd miss things. Constrained random lets you define rules and constraints, and then the tools generate vast numbers of random but valid test scenarios. This is incredibly powerful for hitting corner cases you might never think of manually.
So it explores the possibilities automatically.
Intelligently explores them. Then there's functional coverage. This isn't just about running code, it's about defining specific features or scenarios from the spec and measuring whether your tests actually exercise them.
Making sure you tested what you meant to test.
Exactly. And assertions are like little checks embedded directly in the design or test bench code that constantly monitor for correct behavior during simulation. If an assertion fails, you know immediately something's wrong, often pinpointing the issue.
So UVM provides the structure. What do the pieces inside a UVM test bench look like?
Conceptually, you have components like an agent, which usually handles everything related to a specific interface or protocol. Inside that, you'll find a driver, which takes abstract commands, called transactions, and wiggles the actual pins on the design under test, DUT.
Weebles the pins, kind of.
A monitor watches the DUT's pins and activity, gathering information and checking for errors. A sequencer controls the flow of those transactions, directing what tests or stimuli the driver should apply. And often a scoreboard compares the actual results observed by the monitor with expected results, perhaps from a reference model, to declare pass or fail.
Like a whole factory floor for testing.
It's a very structured, reusable approach. And related to those embedded checks we mentioned, there's assertion-based verification, ABV, which focuses heavily on using those assertions throughout the design and verification process. They act as executable specifications catching bugs very close to the source.
Okay, so you run all these tests, random stimulus, assertions. How do you know when you're done? How do you know you've tested enough?
Ah, the million-dollar question. That's where coverage closure comes in. Coverage metrics quantify how thoroughly the design has been exercised.
You mentioned functional coverage. Is that the main one?
It's a crucial one, but there are two main types you look at together. Code coverage measures which lines of your RTL code were actually executed during simulation. Did you hit this if statement, this case statement?
Okay, simple execution count.
Right. But then there's functional coverage, which is user-defined. You, the verification engineer, create metrics based on the design specification. Did we test this specific mode of operation? Did we see this combination of inputs? Did this FIFO get full?
Ah, so code coverage checks the code, functional coverage checks the features.
Exactly. And they are complementary. You could have 100% code coverage. Every single line of code ran, but still have only 50% functional coverage because you didn't actually test all the critical features described in the spec. You need both to be high.
I see. And the benefits of tracking coverage seem obvious then.
Huge. Early detection of untested areas, focusing your verification effort where it's needed most, mitigating the risk of shipping bugs, increasing efficiency, and ultimately getting to market faster with higher confidence.
How do teams actually achieve coverage closure? Just run more random tests?
Sometimes more random helps, but often you need more targeted strategies. You analyze the coverage reports to find the holes, the areas you haven't hit. Then you might write specific directed tests to target those difficult-to-reach corner cases. You set clear sign-off criteria, maybe 100% functional coverage, 100% code coverage, or close to it, with waivers for unreachable code, and all tests passing in regression. But honestly, achieving full closure, especially on complex designs, can be incredibly difficult and time-consuming. It's a constant battle.
Which brings us to the ongoing challenges. Even with all these advanced methods, it's still tough. What are the big hurdles engineers face in RTL design and verification today?
Well, in RTL design itself, timing closure is a perennial headache, making sure all the signals get where they need to go within the clock cycle time. As frequencies go up, this gets exponentially harder. Every picosecond counts.
Yeah, faster clocks mean less time for signals to travel.
Exactly. Power consumption is another huge one, especially for anything battery-powered. Designers use techniques like clock gating and power gating, shutting down parts of the chip, but managing leakage and dynamic power is complex.
And you mentioned something earlier, clock domain crossing, or CDC.
Ah, yes, CDC. That's a tricky one. When you have different parts of the chip running on different unsynchronized clocks, passing data between them safely is critical. Get it wrong, and you risk metastability, that unstable state we talked about, or data corruption. These bugs could be incredibly hard to find and debug.
Okay, those are design challenges. What about verification specifically?
The biggest challenge is probably scalability. Designs are just so massive now, the number of possible states is astronomical. You simply cannot simulate every possibility. It's computationally intractable.
So you can't guarantee you've found everything.
Not through simulation alone. This leads to the challenge of corner cases. How do you find and test those rare but critical combinations of events that cause failures? Random testing helps, but finding all of them is tough.
The needle's in the haystack.
Exactly. And when you do find a bug, especially late in the process, debugging becomes a major bottleneck. Figuring out the root cause of a failure in a billion-gate design from a simulation trace, it can take days or weeks. It's often estimated that debugging consumes up to half the total verification time.
Wow, half the time just finding the root cause. So given these huge challenges, complexity, scalability, corner cases, debugging what's next, how is the industry trying to tackle this? Is there a new frontier?
There definitely is. What's really changing the game now is the increasing integration of artificial intelligence, AI, and machine learning, ML, into the design and verification workflow.
AI and ML in chip design. Okay, that's interesting.
It's a true paradigm shift. These aren't just buzzwords. They're being applied to solve real problems that are becoming too complex for traditional methods alone.
How specifically is AML helping in verification tackling those bottlenecks?
Several ways. For test bench generation and stimulus optimization, AI can learn from past simulations and intelligently guide the constrained random testing towards uncovered parts of the design state space, hitting coverage holes much faster.
So smarter random testing.
Much smarter. For coverage analysis and bug prediction, ML models can analyze huge amounts of simulation data, coverage metrics, even design code to predict where bugs are most likely to be hiding, helping teams prioritize their debugging effort.
Focusing the searchlight.
Right. And AI can also help enhance formal verification by automatically generating candidate properties or assertions to prove, which can significantly speed up the setup for those formal methods. The key benefits everyone's chasing are clear. Reduce the overall time to market, improve the predictability of silicon success, find bugs earlier when they're cheaper to fix, and potentially optimize designs in ways humans might miss.
But I imagine adopting AI isn't trivial. What are the hurdles?
Oh, definitely challenges. Data scarcity is one. You need lots of good, relevant data to train effective ML models, and that can be hard to come by initially. The computational overheads for training can be significant. Integration complexity, fitting these new AML tools smoothly into existing complex EDA flows is a major engineering task.
Right, making it work with the existing tools.
And a big one is the black box problem. Some ML models can be hard to interpret. Why did it make that prediction? When you need absolute certainty, like in chip design, that lack of explainability can be a barrier to trust and adoption.
Especially for safety-critical stuff.
Absolutely. But looking ahead, the trend is clear. We're moving towards more end-to-end AI-driven workflows, maybe real-time adaptive verification systems that learn and adjust as they run, perhaps even foundation models like LLMs, but for silicon design, assisting with RTL generation or optimization.
A smart design ecosystem.
That's the goal. Ultimately aiming for faster, more reliable design, maybe even getting closer to that dream of zero-bug silicon.
So wrapping this up, it's been an incredible journey from just an idea down through RTL, synthesis, layout, and this massive verification effort to a working chip. RTL is that crucial blueprint layer.
The essential abstraction, yeah.
And verification, taking up that huge chunk of the cycle, is just absolutely non-negotiable for getting working silicon first time. Our digital world literally depends on it.
And those robust methodologies, UVM, assertions, coverage, are the bedrock. Combining those with strategic adoption of AI and ML is really how the industry is tackling future challenges and pushing the envelope.
And it's worth mentioning again for anyone listening, the semiconductor industry is booming, and the demand for skilled verification engineers is incredibly high. It means great career opportunities, strong salaries. It's a field that desperately needs talented people.
Yeah.
So here's a final thought to leave you with. As AI keeps weaving itself deeper into complex fields like chip design, how do you think those traditional roles of designer and verifier might morph or blend? What new kinds of creative challenges or maybe even opportunities will emerge for the human engineers working alongside these AI tools?
That's a fascinating question. But one thing is certain. The ongoing growth and the demand for skilled engineers highlight just how vital these disciplines are for shaping the future of all electronics.
That's all for this deep dive. We hope you enjoyed this look into the intricate world of chip design and verification. Keep diving deep.